Okay, welcome everyone to lecture number 7 of this course on nonlinear and adaptive control. So far what we have seen is the basic framework of adaptive control. We have seen direct adaptive control, indirect adaptive control. We started off with a scalar case and then we extended that to the vector case for plants which have parametric uncertainty, that is where the system matrices or the control input matrix are unknown. It's easier if the control input matrix is known, as we saw in the vector case where the matrix B was required to be known for the analysis to be done in a tractable way. But there are cases where you could do analysis and control design for systems where both A and B matrices are unknown. So, that is left for you as an exercise. So, today in this class we will focus on systems with disturbances, unmodeled dynamics, unstructured uncertainties. So, there does the MRAC that we have designed so far work where we have plants with such effects. So, we will start off with a slight detour. So, I get these questions many times. Students ask why do a nonlinear control analysis for linear systems. So far in this course we have covered LTI systems. MRAC basically concerns control of these linear systems, but we have used nonlinear analysis and design tools for developing the MRAC. So, a natural question arises, if it is a linear system, why not use linear control tools. So, I just want to clarify that question in this class before we move on to robust adaptive control. So, so why use nonlinear analysis for MRAC? Okay. So, say you have an LTI plant. I am taking a scalar case, x dot equals A x plus B u, and the reference model is again an LTI system, x m dot equals A m x m plus B m r. So, we have done this many times in this course. So, you should this system should be familiar to you now. So, now this is open loop linear system. So, we have not really designed the controller yet, and it is an LTI system. Now, if we design our U as a model reference adaptive controller, such as what we have done in this class before, k x hat x plus k r hat r, where we have these usual matching conditions that there exist k x and k r such that a plus b k x is equal to a m and b k r equal to b m. Anyways, this is just for completeness sake, but the point that I want to make is that when you write down the closed loop error system, that is when things get interesting. So, we define the error as x minus x m, and then we write down the expression for the error dynamics. So, the closed loop in fact, the tracking error, I should be very specific here, because we have the parameter estimation error as well in this case. So, tracking error dynamics are given by E dot equals A m E minus bkx tilde x minus bkr tilde r. Okay. So, we can also go ahead and write down the dynamics for the parameter estimation errors. So, parameter because once we introduce these parameter estimates through our controller, we get these two extra states kx tilde and kr tilde, and when we consider the overall system, we need to consider the parameter estimation errors also as our overall system dynamics. So, kx tilde dot is given as bxc. This is what we had designed, and kr tilde dot is given by b r e. So, this is assuming that b is known, right. So, now here we want to express this as a state space system. So, we look at the right hand side. So, of course, we know that the states are E, kx tilde and kr tilde. Now, if we can express the right hand side in the form ax plus b plus br or something like that, then we can say it's a linear system, and we could use linear design tools for analysis, for stability analysis. So, let's see what the right hand side here comes out to be. So, what we see here is that we can replace certain terms on the right hand side. So, let's rewrite the tracking error dynamics in terms of E. So, we replace x by E plus xm. So, what we get is minus b kx tilde E minus b kx tilde xm minus b kr tilde r, and kx tilde dot also we similarly modify. So, we replace x by e plus xm, and what we get is b e square plus b xm e, and kr tilde dot as b r e. Okay. So, this is the overall closed loop error dynamics. And to prove that E is bounded or E goes to 0, we need to also consider the dynamics of the parameter estimation error kx tilde and kr tilde. And because now they are included in the extended state space, we have to see whether the right hand side is indeed a linear system, and we have terms here like b e square kx tilde times c, a product of states. So, these terms indicate that this is no longer a linear system, and we cannot go ahead with linear design tool unless you want to linearize, but here we want to do the analysis in a global manner. So, we want to go ahead with nonlinear control tools. So, this explains why the overall state space, the extended state space indicates a nonlinear system, and that motivates the need for doing nonlinear design in this case. So, I hope it is clear why we are using Lyapunov stability analysis instead of say looking at just the eigenvalues of the A matrix for a linear system. Okay, so now we can move on to the topic of this class. So let me just write the the topic. So this is adaptive control under plant uncertainty unmodeled dynamics and external disturbances. Okay, so let's consider a mass spring damper system. So this is probably one of the simplest systems that you could consider, but that just helps in illustrating the point that I am trying to make here. So we've got a damper, we have got a spring, and we have mass, and there is a force which is acting on this mass, which is denoted by F. So we know that if this is a linear system, then we could write down the equation of motion as Bx dot plus Kx equals F. Now, if I ask you to do an adaptive controller for this system to such that the state x, which is the position of the mass, tracks xd, which is a desired trajectory, then you could use what we had done in the last class, where we had developed an adaptive controller for a command tracking problem instead of an MRAC problem. You could use similar method to design an adaptive controller for this command tracking problem, and it would be a straightforward use of what we had done last time. So here we consider that m, b and k, which are the mass, the damping constant, the spring constant, are unknown constants, and we can still go ahead and design the adaptive controller for this case. So this case we can design an adaptive controller, right? Now we know that real systems are not exactly linear. There is some non-linearity or the other. So now if I modify this mass spring damper system and include some uncertain terms like say friction and say a nonlinear spring. So let us say the dynamics get modified as mx double dot plus bx dot plus kx. So in addition to that, we also have say some friction affecting the movement of this mass, and let us say this is a Coulomb friction. So we model this as Bc sine of x dot, and then we have a nonlinear spring term. Okay. So let us say that these can be written as some delta. Okay, so this delta denotes a nonlinear uncertainty. Now, can we design an adaptive controller for this case using the methods that we have done so far? So, we have to look closely here. So, this delta consists of the Coulomb friction term as well as this nonlinear spring term. So, what we know here is that that this is indeed the Coulomb friction, and we have modeled it like this, and the nonlinear spring has this cubic term in it. The constants B c and K n are in fact unknown, but their signum of x dot and x cube are things that we know. So, this kind of an uncertainty falls in the category of a structured uncertainty. So, the structure is known, the structure of the uncertainty is known. Okay. In fact, we can further qualify this by saying that this structured uncertainty is linear in the parameters. Okay. So, this is linear in the parameters. What do we mean by that? Is that we can separate out the unknown constants in a linear way. So, we can write delta as w of x dot transpose theta, where this w is a regressor of known terms. So, here what are the known terms? The known terms here are signum of x dot. So, these terms may be nonlinear, and x cube, these are nonlinear terms, but we can separate out the unknown constant terms from these known terms in a linear way. So, the unknown constants come out as theta, and this is w transpose. So, have we handled such kind of uncertainties before? Yes, we have. In the previous class, we considered a case where we had a linear system, and in addition to that we had structured uncertainty which is linear in the parameters. So, such cases can also be handled using our classical adaptive control approaches. So, we can say that structured uncertainty which is linear in the parameters can also be handled with the with our existing tools, or the tools that we have done in the class so far. Okay, so, number 3. So, number 3 could be, we have delta which includes a slightly complicated model of friction. So, let us say we have mx double dot plus bx dot plus kx plus delta f is equal to f. So, delta f refers to another model of friction which is slightly more complicated, but it is commonly used, and it is given by f c signum of x dot 1 minus exponential of minus x dot square divided by V s plus f s signum of x dot 1 minus e to the power minus x dot square divided by V s. So, V s square, sorry, V s square, and then we have f v x dot. Okay. So, the first term represents the Coulomb friction. So, this is Coulomb friction. This term represents the static friction, and this term represents the viscous friction. Okay, so, we have 4 unknown constants here, f c, f s, f v and v s. V h is a Strybeck parameter. So, all these unknown constants are present in this model of friction, but can we separate out these unknown constants from these known terms in a linear way? So, the answer to that question is no. So, in this case, because we have so the viscous friction can be linearly parameterized. So, we have f v times x dot. So, this is in the linear in the parameter form. So, this can be handled with the tools that we have done so far, but what about these two terms? So, signum x dot can be factored out, but then that gets multiplied by this exponential term which has this unknown parameter V s, which unfortunately cannot be factored out in a linear way. So, this kind of model of friction is called nonlinear in the parameter. So, as a short, this is NLIP. The one that we did above was LIP, linear in the parameter. This is nonlinear in the parameter, and it is not straightforward to design adaptive control laws for such cases. So, we have a recent paper where we do a adaptive control design for nonlinearly parameterized plant. So, if you are interested, you can search on Google and you will find the paper. Okay, but the results are not very common. There has been some research, and they are not very elegant, not as elegant as say MRAC or the other adaptive control methods. Okay, so this still falls. So, this is still NLIP structured uncertainty. So, we know the structure of this uncertainty. So, we still call this as a structured uncertainty, although in this case this is NLIP. So, we can't handle this case using the adaptive controllers that we have done so far. Okay. In literature, there have been works which tackle this kind of uncertainty, but not using the tools that we have done. Okay. So, then we come to say number 4. So, number 4 could be unstructured uncertainty. So, where we do not exactly know the structure of uncertainty. You could also talk about unmodeled dynamics. So, there are systems for which we cannot model certain parts, and we call them as the unmodeled dynamics. They may be neglected under normal operating conditions, but maybe under high frequency these modes also may get excited, but for a normal frequency range we may neglect certain dynamics. So, those dynamics which we cannot, which we are not capable of modeling, or which we can safely ignore for the operating conditions, we call them as unmodeled dynamics. And you can also, so these unstructured uncertainty, unmodeled dynamics, and external perturbations, they can actually be clubbed under say D. Okay, so this represents unstructured uncertainty, unmodeled dynamics, or external disturbances. So, of course, this is a very simplistic case where I have considered just an additive uncertainty or an additive disturbance. There may be cases where you have more complicated dynamics involved. for now let us just focus on this additive disturbance. So, there are various ways in which such unmodeled dynamics or uncertainty or external disturbances can be handled, and the most popular are the robust control methods. So, we take the worst case scenario for such uncertainty or such dynamics, and then we design controllers which account for this worst case scenario and still be still able to maintain stability. So, that is a class of robust controllers. Can we use the adaptive control techniques that we have studied so far for this scenario? So, here we do not know anything, we do not know the structure of this disturbance D. So, in a mass spring damper system, this could be like an if you are say pushing the mass, you are giving some external stimulus to the mass, and those forces we cannot model. We do not know what is the structure of those external perturbations. So, we club everything under this term D. So, can we design adaptive controllers for such a scenario? So, using the existing techniques, of course, since we do not know the structure of D, we can not design. So, that is the focus of this lecture, that we would like to design adaptive control laws which can work in scenarios where you have external disturbances, and that is a fairly realistic scenario, because these are terms where which in real systems you don't know these terms, but maybe by some experimentation we can say that we can upper bound these terms. So, if I say that the upper bound of such terms is known, we may be able to handle such terms using robust adaptive control methods. So, let us begin talking about these robust adaptive controllers in a general setting. So, again we go back to the plant model that we have, start equals A x plus B u. So, let us say this is the plant, the reference model is given by basically copy paste of stuff that we have done many times before. Okay. So, for this plant and for this reference model, we know what is the MRAC, right. We design as Kx plus Kr hat R. Now, if I ask the question that suppose this plant experiences certain external perturbation, and we denote that by D. Okay. So, let us just also make this more complete by mentioning the dimensions here. And D is Rn. Okay. So, all we know about this disturbance term D is that it is bounded, it is uniformly bounded. So, this D is, and D bar is a positive constant. Okay. And here A m and B m have appropriate dimensions. A m is Hurwitz and R is a bounded reference signal. Okay. So, and we also follow the matching conditions. So, I am not going to write that again. Now, let us see if the same model reference adaptive controller that we have designed for the disturbance free case works in case the plant experiences a disturbance. So, as a control engineer, I do not I design my controller thinking that there is no disturbance, and the model of the plant is this x dot equals A x plus B u, even though A and B may be unknown. Okay. But I do not expect this model to be something other than this. Okay. But in real life this may not be true. So, the controller that I designed for this situation, how does it fare when the plant in fact experiences an external disturbance. So, that is the analysis that we are going to do now. Okay. So, again using the similar analysis as before, we can write down the closed loop tracking error system. Okay. E dot as okay. So, this was what we had gotten previously. Now, because of this disturbance term, we have an extra term in our tracking error system, which is D. Okay. So, now we do a Lyapunov analysis. So, let us consider the same Lyapunov function candidate that we had considered before. Of course, you can choose a different Lyapunov function candidate. So, this Lyapunov function candidate has worked for us so far. So, let us just try this out. Okay. This is a trace operator. We have discussed that before. Okay. So, this is the Lyapunov function, and here P is symmetric positive definite solution of the Lyapunov equation. A m p plus p a m transpose is equal to minus q, and q is also positive definite and symmetric, and since a m is Hurwitz, this will have a solution, and that is given by p. Okay. So, so now let us take the so this function is positive definite, readily unbounded, decrescent. We go ahead and take the time derivative. So, I will skip a few steps here. X tilde dot K r tilde transpose gamma r inverse and K r tilde dot. So, these gamma x and gamma r are also positive definite matrices. Okay. So, now we can go ahead and substitute for the error dynamics and in all these terms. So, we substitute for E dot in the first two terms, and then we design K x hat dot and K r hat dot. So, I'm going to skip a few steps here, and I'll come to the expression for V dot. So, V dot is given by minus half E transpose Q E minus X transpose K X tilde transpose B transpose P E minus R. You can go back to the notes and check if we get the same expression, minus trace of K X tilde transpose gamma X inverse K X hat dot minus trace of K R transpose and so this is what we had obtained last time, but there is an additional term this time which is plus E transpose P D. So when we substitute for the aerodynamics here, we see that there is this term D in the aero system, and that shows up here in the Lyapunov function derivative. Okay, so and here of course the control designer assumes that this is a disturbance free case. So the control design is already done. We have already done the the adaptive laws, and they are given as minus gamma X B transpose P E X transpose K R hat dot is minus gamma R B transpose P E R transpose. All right. Okay. So once we substitute for these in these expressions including trace, what we get is V dot as minus half E transpose Q E. So these update law designs will cancel the second and the third terms, and what we get is simply E transpose P D. Okay. So suppose D was 0, then we would have gotten minus half E transpose Q E, and we would have concluded that this was negative semi definite, and this would lead to Lyapunov stability. We could go ahead and prove that E goes to 0 using the Barblet's lemma. All signals are bounded and we are happy, right. But just in the case that the plant experiences an external disturbance, is the controller that we have designed robust to such external perturbations? That is the question that we are trying to answer here. So if we look at this term, we do not know the sign of this term, because E can have any sign. It is the error, it is a state, it can have any sign, positive, negative, we do not know. The P is of course a constant positive definite matrix. D is a disturbance term which is a function of time, again it can have any sign. So this term is in fact sign indeterminate, we can't say what the sign is. So the best that we can do with such terms is to upper bound it. So we say that V dot is upper bounded as minus half E transpose Q E plus so in fact what we can do here is that we can also upper bound the first term. So what we get is minus lambda min. So the minimum eigenvalue of Q. So this expression will upper bound the first term, and then upper bounding the second term, we have because here we have a positive sign. So the maximum eigenvalue of the P matrix times the norm of E times the norm of D, which can be upper bounded as D bar. So this is what we get here. Okay. So what can we say here? The first term of course is not a problem because it is negative. The second term is a positive term. Now, what we have to see here is, can we dominate the second term with the first term. Okay. If we can completely dominate, then of course, we can still say that V dot is less than equal to 0, and we could still conclude Lyapunov stability. Let us see if we can do that. So, it does not seem very clear how we would be able to do that. So, V dot, what we can say is that we take the lambda max okay. So, this is what we get. Okay. Now, what we can see here is that if the term in the bracket, in the square bracket, is positive, then we can say that V dot is less than equal to 0, and we can conclude Lyapunov stability. So, so we can consider two cases here. So, case 1 is when norm of E is greater than 2 lambda max over lambda min times t bar. So, suppose this case, this is true. So, what this would lead to is V dot being less than equal to 0. So, which means that V dot is negative semi definite, and we can conclude that V is bounded, right, because V is positive and V dot is less than equal to 0. So, V is bounded, and since V is bounded, we can further say that E of t, k x tilde of t and k r tilde of t are also bounded. Okay. So, this is a good situation to be in, but what happens when E is less than equal to 2 lambda max? In fact, I think what we can do is we can have the equality here, right. So, what if this case 2 is true, that the tracking error is, the norm of the tracking error is less than this constant, right. All the terms here are constant terms. We have the maximum eigenvalue of p, minimum eigenvalue of q, and the upper bound on the disturbance. So, if the tracking error goes below this value, then the term in the bracket in fact becomes less than 0, and then V dot becomes less than equal to some positive number, right. So, what that means is that we cannot really conclude about V dot. It could be negative, it could be positive. All we know is that V dot is less than equal to some positive number. Okay. So, we can't conclude from here, and we can't say that V of t is bounded. We can't say that, we can't guarantee that V is in fact bounded. But what we can say from this case is that the tracking error is bounded, because that is the case that we are talking about, that the tracking error goes below a certain value. So, E of t is bounded, But what about the parameter estimation errors kx tilde and kr tilde in this case? So, in this case we can't really guarantee that the parameter estimation errors are bounded. In fact, you could say that the parameter estimation errors can go unbounded in the presence of disturbances. So, we cannot guarantee using this Lyapunov analysis that they are in fact bounded. In case 1, we could say that both the tracking error and the parameter estimation errors are bounded, but in case 2, which can also happen, we can't say that the parameter estimation errors are bounded. And what that means is that the controller, which consists of the estimates, the parameter estimates, can also go unbounded, which is a highly undesirable scenario. We of course do not want any signals in our system to be unbounded. Here in fact the control can also go unbounded. So, it is a very it's a scenario that should not happen, and this phenomena is in fact called as parameter drift. So, the adaptive controller that we have designed is not robust to disturbances. So, the parameter estimates may drift away and go unbounded in the presence of external bounded disturbances. So, this phenomena came to light many years ago when a NASA flight crashed, and there were lots of investigations into the reasons why that could have happened. And one of the things that came out of that investigation was that if the model is not perfect and there are some unmodeled dynamics or some external disturbances, that can lead to certain parameters to go unbounded and can lead to a catastrophe, which is what happened. So, this is a very important case in adaptive control. We need to be able to ensure that the adaptive controllers are robust. Okay. So, so this MRAC that we have designed is of course not robust. So, is not robust to external disturbances, unfortunately. So, how to overcome this parameter drift? That is the next question to ask. So, so one way that that we can overcome this parameter drift is if somehow we could cancel the effect of this disturbance term from the closed loop error dynamics. So, if we go back to our closed loop error system, so we have this term d in E dot, right. So, if we can say add an additional term here in the controller, which we call as a robust term, and that cancels the effect of this disturbance, then maybe we can handle such scenarios. So, that means we have to consider a non-certainty equivalence controller, okay, and we can surely design such controllers where we have an extra robust term in addition to the nominal MRAC. Okay. So, such robust terms, for example sliding mode, can cancel the effect of these disturbances, and can still guarantee stability. So that is out of scope of this class, because we are only concerned with adaptive controllers here. So, we are not going to use a robust control law, rather we are going to use a robust adaptive law. So there are two ways in which to handle such cases. One, of course, is that we robustify the control law. So, we add, in addition to the nominal, we add some robust term. And how do you design this robust term? That is not the focus of this course. So, out of scope of this course. So, number 2 is we robustify the adaptive law. So, when I say robustify, I mean that we consider the worst case scenario for this disturbance, and we develop a controller which is highly conservative. So, the performance might degrade, but more important than performance is stability. So, the first requirement for a control system is that it should be stable, and it should be stable under uncertainty, under disturbance, and then of course, we look at performance. So, a robust adaptive law may not be as well performing as the laws that we have designed previously, but because of this robust element, we might be able to account for the effect of these external disturbances. So, which is what we will do in the next lecture or two. So, the first technique that we will consider is dead zone. So, this is we are trying to modify the adaptive laws. So, these are techniques which fall under the category of robust adaptive control. Okay. So, dead zone is a very intuitive idea. So, if we go back to the analysis that we have done previously about how disturbance affects an MRAC system, we see that case 1 is all right, because here we could prove that all the errors are bounded. The problem is with case 2, where we could not prove that the parameter estimation errors are in fact bounded. So, k x tilde and k r tilde being bounded, we do not know, okay, although we could say that tracking error is bounded, and because we can't guarantee this, one way in which we can make sure that in this case the estimates are bounded is by stopping the adaptation for case 2. So, in case 1 we just follow the adaptive law that came out from the Lyapunov analysis, and when the error goes below a certain bound, then we stop the adaptation. So, the adaptive the parameter estimates, they stay wherever they are, and we do not go ahead with their adaptation. So, that will make sure that these estimates are in fact not going to grow unbounded, and so we prevent the case of parameter drift by introducing a dead zone, a zone in which there is no adaptation. Okay. So, so let us just do a recap. So, case 1 was okay, because we could guarantee that the tracking error and the parameter estimation errors, they are all bounded. So, this case was okay. For case 2, we stop the adaptation of k x hat and k r hat. So, what that means is that kx hat and kr hat, they stay constant in case 2, and which means that they will not be unbounded. So, what we have to do is we have to modify the update law as kx hat dot will be now in 2 cases. So, we follow the same law that was used before. So, here we say that this is a case where the tracking error is larger than a certain threshold. So, we call that as the dead zone. We can of course take a dead zone which is larger than this. Okay, so, this was else we say that kx hat dot is in fact 0, and this is kx hat is a matrix, it is an m cross n matrix. So, we just use those dimensions here. So, if the tracking error is larger than the dead zone that we have used here, then we follow the adaptive law, the classical adaptive law, and when the tracking error falls below that value, then we say that kx hat dot is equal to 0. Okay. And similarly, we do it for kr hat dot. Okay. So, we use a similar adaptive law as we had done for kx hat. So, what happens to the adaptation in both the scenarios? So, let us just look at a pictorial representation here. So, this is norm of E versus time, and in the case where so let us also have the dead zone. So, this is 2 lambda max over lambda min of q times d bar. So, this is our dead zone. Okay. So, anything above this, suppose the error starts above the dead zone, then of course, we will follow the classical adaptive laws, and V dot in this case is less than equal to 0, okay, which means that E kx tilde and kr tilde are bounded. Okay. Now, when the tracking error tries to go below the dead zone, that is when we say that we stop the updation. So, in this case we say that kx hat dot is 0 and kr hat dot is 0. So, at this time instant, say t1, whatever value that kx hat and kr hat had, they will stay the same as long as the error stays within this dead zone. Now, when the error moves out of this dead zone, we again start the updation of kx hat and kr hat. So, during this time, the value of kx hat will be what it was at t1, and the value of kr hat will be what it was at time t1. Okay. Of course, once the error goes outside of the dead zone, we start the updation adaptation of kx hat and kr hat using the classical update loss, the unmodified update loss. So, with this strategy, what we have made sure is that for all time the error, the tracking error and the parameter estimation errors are bounded. So, E of t, kx tilde of t and kr tilde of t, they stay bounded. So, which means that the control input u of t also remains bounded. So, here interesting thing to note here is that because our cases here depend upon the evaluation of the dead zone, and for that we need to know the upper bound on the disturbance. So, we say that for this dead zone modification of the adaptive loss, we need to know the upper bound on the disturbance. So, for dead zone modification based update loss, the upper bound of the disturbance is required to be known. So, another curious aspect of this dead zone modification is that suppose we make this modification of the update law, and thinking that there would be a disturbance d whose upper bound is d bar, but say in reality there is no such disturbance. So, the plant just follows x dot equals a x plus b u, and the control designer of course thought that there might be a disturbance with an upper bound d bar. So, the adverse effect of a in the disturbance free case is that we no longer would be able to guarantee that the tracking error asymptotically goes to 0. So, this is what we had achieved using the unmodified adaptive laws done previously, where we use the Bartlett's lemma to prove that E of t goes to 0 as t goes to infinity. Now, here since we have modified these update laws, even in the case where say the disturbance is not present, in the disturbance free case, we will not be able to guarantee because of this modification that the tracking error goes to 0. Okay. So, this of course degrades the performance of the adaptive controller, especially in the disturbance free case, but what it provides us is its robustness to external disturbances whose upper bound we know. Okay. So, this is the first of the 4 modifications that we will make to the adaptive laws to make it robust to the effects of external disturbances. So, we will continue with the robust adaptive control in the next class. Thank you.